All right, welcome. My name is John Vert. I'm an architect in the Windows HPC server group. I'm here to talk today about doing some data-intensive computing. One of the big problems we have in HPC is this increasing tsunami of data, both by the more computational power we have available in HPC clusters at bigger scale and faster processors, create finer grained models, create more data. We also have an explosion of sensor data. As the sensors are also on an exponential growth curve, getting more resolution, higher resolution data acquisition, and that's creating even more data that we then need to do computation around. And also another driver here is some of these internet scale services like search, which are generating terabytes, petabytes of data, server logs, things like that people want to mine through, find correlations, find relationships. So DryadLINQ is a framework for doing data-intensive computing, loosely coupled parallel computing on top of HPC server in this case. And this is an incubation project. It's a collaboration between some people in Microsoft Research, a couple different groups there, HPC server team, as well as some people in the Search and Azure groups. So this is not a production product code yet. It's all an incubation. You can go to the site and download this, try it for yourselves, and give us some feedback. My main goal here is get this stuff out there, get some feedback in the programming model, and help us understand how we should bring this to market and product. So there's a lot of moving parts here. It's a big distributed system, complicated layers. HPC Server 2008 at the bottom does the basic job scheduling, deployment of compute nodes, management. There's some other stuff in the HPC server product I won't go into, but in this framework, it's mainly used as management infrastructure and for the job submission and executing the tasks. Dryad is a distributed runtime that runs on the HPC server cluster. It's a data flow scheduler. It gives you some reliability characteristics, ability to restart failed tasks, as well as extreme scale out over partitioned data. Then LINQ, I think probably most of the people in this room are familiar or heard something about LINQ in this PDC or previous ones. It's a .NET extensions to both language and the framework, designed to give you declarative query capabilities across data sets, whether those are objects in memory, on disk, or in a structured store like a SQL server. P-Link is a new technology that's coming out with .NET Framework 4. There's a talk on this later in the week on how to get parallelism on a multi-core machine using LINQ. If you're interested in that, I highly recommend that talk. I think it's Thursday morning. And then DryadLINQ is going to be the main focus of my talk today. And that really takes the LINQ ease of programming to the scale-out partition data, data flow stuff that Dryad supports, and brings that together with the standard .NET programming model. So if you put it all together, you can get one of these nice architectural pictures, the HPC job scheduler and HPC server on the bottom, Dryad running on top of that to do the actual execution of the graph. And then your .NET application running on a client, talking to the DryadLINQ framework, which then will send the job off to the cluster to run and get the results back from that. So Dryad is the main execution here. This is designed to really be a flexible distributed execution environment for a data flow. We model the computation as a big graph with dependency graph and execute different vertices of that dependency graph across the cluster. And we can restart things, get high availability if things fail. We can run multiple instances of vertices. If one's running slow, we can start up with some additional ones. And it gives you a very flexible, very rich environment for building up these data flow graphs, instantiating them on a cluster, running them, tracking their progress. It also handles distributing the code, writing the code to where the data lives, so you don't have to move all this data around, because the killer thing when you have these huge data sets is you don't ever want to have to copy that data unless you have to. You want to take your computation, move it to where the data lives, run it locally, especially in a typical data center or cloud environment where you may have very oversubscribed network switches. You don't want to be moving data across racks, across machine boundaries unless you really have to. So Dryad has a lot of optimizations to reduce the amount of data movement that has to happen during this data flow computation. So what does a Dryad job look like? You know, this is not really a familiar picture probably. Most people sitting down writing code think of their problem as this way. But this is the way Dryad models your computation. You have a set of inputs at the top. That's a computation that's going to happen in that vertex of the graph. And it's going to flow the results of that computation out across a channel. That channel could be just a file on disk. We'll write the output to a file and feed that file into the next vertex in the graph. It could be a direct connection, a pipe or FIFO network connection. So you could actually run these two vertices at the same time and pipe the results directly over the network. But again, this is not necessarily a programming model that people want to think about having to, manage wiring up all these vertices by hand, building these channels, putting the different semantics on that. So a more natural way to think of a Dryad job that's familiar to a lot of people is really as a two-dimensional version of this classic Unix one-dimensional pipeline. I'm sure everybody's familiar with this model. You take a file, you pipe it into grep and send the output of grep into the next stage, which is set or sort, and you do some filtering, some modification of the data as it flows along the pipeline. Dryad really is the same kind of thing, only we've added a second dimension, which is a scale out. So rather than running one instance of grep across 1,000 different files, you can start 1,000 different instances of the grep process in parallel, each processing one file and producing one file as an output. So, and although you've built this scale-out two-dimensional pipeline, Dryad has the ability to multiplex the different vertices across different machines in the graph. So even though I might have 1,000 nodes in this graph that need to run, I could run that graph on a cluster which only had 10 nodes, and we just cycle the vertices through those nodes as they complete, bring in the next set. And this means you're very flexible about the amount of computation you have. You can grow or shrink the pool of machines in your cluster dynamically, and the graph execution will expand or shrink to fit what you have available. So this is a really important feature when you're running at very large scale, because you're going to have machines that fail. When you're running at 1,000, 10,000 node scales, you got to expect machines will die, hard disks will die, networks will go down, switches will go down. You need to have the flexibility to adapt to that without having to restart the whole computation from scratch and progress in incremental chunks. So LINQ is a key to the .NET data model here, the declarative extensions to C#, VB.NET. If you're not familiar with LINQ, it's basically a syntax that gives you iteration, selection, filtering, modification of data sets, whether that data set lives in memory as a set of objects in a list or a hash table, whether it lives in a database like SQL Server using LINQ to SQL, or it's XML structured data in a file. You can use LINQ to XML to, in the same way, pull out the data you're interested in, filter it, make operations on that, and get back a result set. And PLINQ is built on top of LINQ, and this is the idea here is we have this nice declarative model for doing data. We can see ahead of time what the query is going to be. We can see what the objects that are going to be input and the operations that are going to be done on it. We actually have the ability at runtime to partition up that query, run it in parallel on multiple threads within the process, bring the result right back into your application. So without even having to rewrite your application or think about threads or locking or anything like this, you can get a pretty good benefit from multi-core on some of these LINQ queries. And it's the same set of query operators you'd use for linked objects. Operates on the same IEnumerable T data sets that linked objects depends on. And you just simply have to add the as parallel operator to kick it into the PLINQ operation. And a similar, my batteries are going dead. In a similar vein, a DryadLINQ is designed to take the same style, declarative programming style that you got in LINQ and PLINQ, and bring that to a cluster. So now, rather than having parallelization across multiple cores in a process, you've actually spread that computation out across multiple nodes in the cluster. We can do the query plan and split the partition the data out across the machines you have available, and split the query out across those machines, bring it to where the data is. And then even on the machine itself, we'll use PLINQ underneath to get multi-core parallelism. Every server you buy today probably has 8, 16 cores in it. So it's really important to be able to take advantage of all of those at a very fine-grained level. And PLINQ is a really easy way for us to just flip on the PLINQ switch and automatically take advantage of the resources there. And again, you get all the same benefits that PLINQ have, the full integration with Visual Studio, the .NET underneath, the full type safety. DryadLINQ also will do automatic serialization of your objects for you. We have to, we're going to spread out this query and this data across the clusters. We have to be able to take your objects, serialize them either into a disk or over the network, and deserialize them on the other end in a different process to run it. So we've really broken out of the process boundary that PLINQ operates in, and so we have to worry about moving these objects around and serializing them. And then another key feature of DryadLINQ is because the nature of LINQ is it's a very lazy computation model. You lay out your query, but it's not ever actually executed until you pull the first result from that query. At that point, the underlying runtime can see everything you want to do. It can see the entire query. It can do some optimizations on that query. It can do some static optimizations to improve locality. It can do some pipelining to combine multiple vertices into one and prevent having to ship that data around. And then there's also additional optimizations it can do at runtime based on the shape of your data and how it's partitioned. So it's a really rich way that we can really see the intent of what the programmer wants to do and optimize what's going to happen based on that intent rather than having the programmer have to explicitly say at every step what the parallelization is. We can discover that and act on it and do the right thing for the programmer. So how do we get from this nice world of LINQ onto this messy world of these graphs running on these clusters? This example of a pretty simple LINQ query. This is kind of the hello world of LINQ. We're going to filter out some stuff and create some new log entries. And we'll get into some more details in this query later. But once you start to pull answers from this query, the DryadLINQ query plan generation is going to kick in. It's going to take this query. It's going to look at it. It's going to do some optimizations around it. It's going to actually generate code that's going to run in each of these vertices. And it's going to generate serialization and deserialization code for the objects that are referenced by this query. And it's going to produce a couple outputs. We'll dig into what the outputs look like later so you can debug these things when they go wrong because it can get kind of messy sometimes. And hand those off to Dryad and the HPC job scheduler for execution. Dryad is going to look at that query plan. It's going to look at the data set that was input and where that data lives on the cluster. It's going to scale that query plan out in the second dimension across the partitioned data. And then it's going to talk to the HPC job scheduler, instantiate the code on the clusters, and actually execute the graph. So this is our simple LINQ query. This is the hello world, I think, of LINQ. You may have seen this in a few other presentations. But we're doing a simple filtering operation here. We've got a set of baby info objects that are an IEnumerable generic type. And we're just going to take from that set, we're going to look for certain babies that were born with a given name and a given state in any particular date range. So we've got a data set that's input from baby and babies, and then we'll do a filter operation. The where clause is going to filter out just the babies that match the criteria we want. And we're going to sort that set, and then return the sorted set to the code. So you can see this looks very familiar if you're used to LINQ. This is natural. If you're used to SQL, this should look very familiar as well. It's very much along the same relational algebra lines of a T-SQL or any other relational programming model. Now we want to take this to a multi-core. I want this thing to run faster. I got thousands and thousands of baby names I want to filter through. I can just throw that as parallel operator in there. All that's going to do is it tells the PLINQ runtime, hey, I want to actually parallelize this query. Do the work for me. PLINQ, when it gets that operator, is going to look at the input set, is going to partition it across the cores in your cluster, divide up the work, do the same filtering, the same sorting that would happen in the serial case, but it's going to do it in parallel, depending on how many cores you have, and merge the results back at the end. Your application didn't have to see or understand the parallelism, just said, hey, I think there's some parallelism here, you guys figure it out. PLINQ will do its best guess to make this thing go faster, and you didn't have to change any of your query, any of your logic here. Now with DryadLINQ, we wanted to have the same kind of model. I want to now take this baby query across billions, trillions of baby names across my huge cluster I have set up to process baby names. And here it's going to be a little different because with DryadLINQ and Dryad, it's all about, the parallelism you get is all about where the data is. And the core data type that DryadLINQ operates on to express that is called a partition table. So instead of an IEnumerable, we've got a partition table of baby info objects. But again, once we set up that partition table, once we have that data on our cluster, we use that partition table to reference the data, and DryadLINQ picks up on the partition table, does the same kind of operation that plink would do to parallelize the query, only this time it's parallelizing it across multiple machines and executing the query plan, handing it to Dryad to do the actual computation in parallel on all the machines where the baby names are stored. So this partition table is kind of a funny thing. It takes some people a little while to wrap their mind around what's a partition table, how do I get one, where does it come from? It's really just a generic container for plain old .NET objects, but it's a scale-out container. So the idea here is it's not stored on one machine or in one place. There's actually multiple chunks of the container are stored on multiple different machines, and the number of machines it's stored on is going to drive the parallelism of the query, because all those machines can operate on their particular slice of the data at the same time. But like all good .NET collections, it derives from IEnumerable, so you can use all the same methods, all the same operations you're used to using on IEnumerable, and it's also an iQueryable, so it works with LINQ and uses the lazy evaluation of LINQ to actually build up a query expression across partition table objects. So once you have one of these partition tables objects, the DryadLINQ operators will consume that, produce an iQueryable T, which will then continue to pass to the next operators and build up the remainder of the LINQ expression. And this partition table T is also a key thing that drives the serialization and deserialization of your objects into those files. Once you declare one of these types, DryadLINQ is going to generate code that can take your whatever object you have that's going to be that type T, write it into the file in compressed form, and read it back in. And this is all done for you. You don't generally have to do too much. There's some hints you can give DryadLINQ about what fields to serialize, and maybe you have some fields that don't need to be serialized or deserialized for this, and you can filter those things out. So you have some knobs you can turn there on the serialization stuff. But the underlying storage of the partition table T isn't necessarily specified. It could be anything. It could be what we have in the release that you can download today, which is what we call a partition file, which is just a set of files across the cluster. It could be a partition SQL table. You could have SQL Server running on each machine in your cluster and multiple tables on each SQL Server and some data set that's spread out across SQL Server. Then you can actually use SQL relational algebra within your DryadLINQ queries and operate on all those SQL servers in parallel. Or it could be a real honest-to-God scale-out cluster file system where the cluster file system itself handles maintaining all the metadata, managing what is where, and chunking up the data into different machines for you. So what Dryad stores in this partition table is mainly your objects, but there's also some metadata in there about what objects are stored, is this table sorted or not, some optimizations it can use later on when it gets one of these tables as input. It says, oh, this thing's already sorted, I don't need to sort it again. That type of metadata is also stored in the structure. Now, a partition file is really the storage that's going to contain a partition table. And this is about the simplest possible thing you could imagine to work for scaling out a file across multiple machines. It's a really simple text file format, and if you open up a partition file, you'll see something that looks just like this. In this case, the first line of the file is the base file name. All the different chunks are going to share that same base name. The second line of the file, 20, that's how many chunks this file is split into. And then there's 20 lines after that, one line for each chunk that represents the chunk number, the size of the chunk, and the machine where that chunk is stored. So you can then take this information and you can construct the actual UNC path to get to that chunk. In this case, you can see we pulled out the machine name, tack on the base name, and tack on the partition number at the end. And it's very straightforward. You can now do some basic arithmetic and find any offset within this partition file, get the UNC name and offset within that within that file that you can reference to get the data. So Dryad knows how to parse these partition files. It knows how to look at one of these partition files, understand where the data is stored, send the code there to operate on each chunk individually. And so You get 20 different chunks stored on 20 different machines. We can now split any query across this partition file into 20 independent executions until we have to do a merge at the end, or any kind of other operator that requires cross-machine interaction. So let's look into an example that's a little more real world here. This is a very typical data-intensive query you might run if you have a big server farm, web logs. What we're going to do is parse these web logs, and we're going to figure out all the web pages that I've accessed and what's the most popular access that I did when I was supposed to be working on my presentation and surfing the net instead. So again, we start off with a partition table. And the get method on the partition table is a static method which takes an input file name and returns a generic type container of the strings. So in this case, the web logs partition file is just a container of string objects. These are just regular old .NET string objects that DryadLINQ knows how to serialize and deserialize from the partition table. And the first thing we're going to do is a little LINQ query that's going to filter these things out. So we're going to filter out the lines that aren't comments, where it doesn't start with a bound sign, we're going to throw it away. If it does, and if it doesn't start with a pound sign, we're going to keep it, and we're going to create a new log entry object from each string. So in this case, we've got our own .NET class called log entry. It's got a constructor that takes a string, and it's going to crack that string using the normal .NET string processing, whatever you want, regex or splits or however you like to crack your strings, and produce some fields. In this case, the fields we're interested in is the username and the web page. So the next step is to go through those log entry objects and keep only entries where I was the one who accessed them. Everything else will just drop on the floor, and we'll produce a new, smaller set that's been filtered. Now we're going to do something a little more interesting. We're actually going to group those. We're going to do a group by operation here on the username. And that's going to take, actually on the web page, that's going to take all the web pages which had the same URL, mash them together into one object, which is going to contain a user page count. So with the user page count object, it's going to have the username, the web page name, and the number of times that particular web page was referenced. So now we've got a new collection, user page count objects. Again, we're going to filter out the only ones that end in HTM, and we're going to sort that so I get the ones that were most frequently accessed at the top, and we're going to return the resulting sorted collection. And I can look at see what the top 10 pages were. You could see what the bottom 10 pages were, or you could just print out the whole collection at this point. So at the end of the day, you end up with a partition table that contains user page count objects that are sorted. And you can then either continue to filter those or just do whatever it is you want to do with them. Now, how does this get into Dryad? What does this look like in that case? Well, part of what DryadLINQ does is it's going to take that query and it's going to build the graph. And the first stage of the graph, of course, is the input partition table set. In this case, we've stored this partition table across 6 machines. There's going to be 6 input vertices that Dryad's going to create in the execution graph. Then the next step, again, the simple filter step, create new log entry objects. This will all happen in parallel across all 6 machines at the same time, and produce 6 new files in a new partition table. And then we're going to filter those log entry objects again, in this case just throwing out the ones that weren't me, and produce a third, smaller set of objects to operate on. And finally, we're going to do something a little more interesting than just filtering and throwing away objects. We're going to actually do a group by here. We're going to group by the user, by the page, and that's actually going to be a hash partition. So this is a case where every vertex is they're going to write out based on the hash of the web page to a different machine. So we've repartitioned the data now across a new data set and created a hash partitioned set. We're going to take that final set and we're going to sort it. Again, this is a similar thing where instead of doing a hash partition, we're actually going to do a range partition and send the data. Every machine is going to have its own chunk of data that is within a particular range. We can then sort sort the data locally, and merge the results and produce the final sorted output set. Still partitioned into multiple chunks across the cluster in case you want to do further operations on it. We try to keep the data spread out, partitioned across the cluster until you really need to materialize it, and then we merge it all back into a single stream. So the query plan generation, obviously the important part of what DryadLINQ does. It really takes the query out of your application. You wrote it in your methods and in your main function, wherever you had it, and it's going to pull out the query from that context. The other things it's going to do is walk through the assemblies you've got loaded, include those, because that query may reference some other type that's in a different assembly. We need to have that on the cluster. We need to be able to identify all those assemblies so we can move them to the cluster for you. And it's also going to, take care of all the lambdas and the closures across the lambdas and bringing the code out. And the other thing it does, I mentioned before, is the code generation to serialize and deserialize your objects to actually create the partition T, materialize that, the partition table T, materialize that from disk, or send it back out to disk. And then it's going to finally take the expression, the query expression you had, and it's going to generate code that's going to run in each of those vertices. So again, it's going to take the actual methods that you called, and it's going to extract those and put those into the compiled code. It's going to ship that assembly out to the cluster as well. And then there's some basic query plan optimizations I mentioned earlier. We have multiple selects in a row. I don't need to write out a new data set for each one. We can just pipeline all of those, do those all in one vertex, and prevent the data being written and read from disk multiple times in that case. And then some other standard database optimizations you can imagine on a query, like hoisting the filters higher up. So if they get done sooner, we'll have less data later to sort, and various things like that. And this is actually what you'd see if you ran that example I gave you. This is the output that DryadLINQ would give you. So you've seen that we've actually got the weblogs.pt is marked as the input to the query. And we've taken the code right from your application and put it into the query. We've created two vertices in this case, super 1 and super 2, super 12, that are going to be the actual methods that are called to execute the query. And DryadLINQ is going to turn that query into an XML file. There's a couple interesting points about this XML file. Up the top there, the resources, that's the list of files that DryadLINQ is going to send to the cluster that we're going to need to run your query on each node in the cluster. So we bundle all those up in the resources section, ship them to the cluster. Dryad takes care of distributing them out to every node. In this case, there's a couple assemblies in there, linked to dryad.dll, wrapper native info DLL, which are just part of DryadLINQ runtime. And system threading DLL, that's the implementation of plink we're using. So we got to send that out to every node so we get the on-node multi-core parallelism. Logdemo.exe, that's your program itself. We have to ship that out so we can reuse the types and code that's within that assembly. And then the other interesting one there is called DryadLINQ0.dll. This is the assembly that DryadLINQ has generated at runtime, which is actually going to run and instantiate your vertices on the cluster. It has all the serialization, deserialization code, as well as the code that's going to do the filtering, the sorting itself. And then you see in the query plan section, there's a set of vertices. We've defined each vertex, what the input of that vertex was, what its children are, what are the methods, the types, and the methods within that type that we need to run to instantiate that vertex. There's a whole bunch of other stuff in this XML file that gets generated. You can browse through it and see. I couldn't fit it all in one slide, so I just tried to call out the most interesting points there. So if you're not sure what your query is doing or how it's created, what the shape of it is, this is a good place to start spelunking through this file that gets generated. And then here's also an example of the C# code that DryadLINQ created, which is going to be compiled at runtime, turned into that DryadLINQ 0 assembly. So you can look at this code, and there's a bunch of boilerplate in there that I've left out. But you can see we've got the same code that we had, the first filter here, source for, we're going to do the dryad where. That's the same code that we had in your application. Those line starts with a pound character. We're going to use that as the filter. Here's the select operation that's going to create the new log entry object. So this is your code that's been ripped out of your program, put into this other assembly that's going to be sent onto the cluster and actually run the vertex. So what kind of stuff can you build what kind of operators do we support? Pretty much all the standard LINQ operators that you're familiar with. Obviously, we already saw the wheres and the selects, select many, order by, group by as well. Also, one really useful thing for a lot of problems is that we actually support joins, so you can do joins across multiple streams on a common key, as well as the standard set algebra, unions, intersection, exceptions, and then a bunch of aggregation functions, counting, maximizing, max-min, and just an arbitrary aggregation where you would define what the aggregation function was. Generally, you want to do some kind of aggregation when you have a large data set. You're not going to want to get back all 10 terabytes. You're looking for certain things, you've filtered certain things, or you've reduced down to the information you want, and you want to pull the aggregation back to your application after it's been aggregated on the cluster. And then there's a couple operators that are specific to DryadLINQ that you won't see outside DryadLINQ. Hash partition and range partition, these are our key operators, one for initially distributing your data to the cluster. And often you may know something about your data set and you know that you want to hash partition it a certain way, or you want to have control over how it gets range partitioned because you have some information about how you want the shape of this query to look when it runs in the cluster. So these give you fine-grained control of how your data gets placed on the different machines. And then there's also a DryadApply operator, which lets you, rather than operating on just a single item at a time, lets you see the whole sequence. So if you want to do a moving average, or you need to see multiple sequences at the same time, do some kind of correlation between two sequences, the DryadApply is a really powerful way you can build that kind of logic in your queries. So people talk a lot about MapReduce. There's a lot of press about MapReduce. The Google paper was obviously very popular. The Hadoop open source implementation of the Google MapReduce is getting a lot of press and mind share. It's simple to do in DryadLINQ. A lot of the tasks that we use DryadLINQ for internally are these kind of map reductions. At the end of the day, you have a mapper function, which takes a sequence as input and turns it into a different sequence. You have a key selector function that takes a sequence and pulls out a specific key. And then you have a reduction that takes that key and that sequence and reduces that down to some other thing. So this is an implementation. You can pass a function that implements that signature into this MapReduce, and boom, you have a MapReduce application. So that's just a quick example of if you have something that's already written in MapReduce or you're thinking in that format, this is how you look at it a little differently, code that into the DryadLINQ framework. There's a little more mind-bending example here. I mentioned earlier in passing that the LINQ queries are lazily evaluated. In this case, we're taking advantage of that to actually build up iteratively a very big, complicated LINQ query. This example here is a k-means clustering algorithm. Clustering is we take a whole set of vectors and we want to find the k centers of all those vectors in space. This is a pretty standard data mining operation. In this case, we'll say k is 10. So given a set of vectors, we want to find 10 points, 10 other vectors, which are the center of those 10 different clumps. The way a k-means clustering algorithm usually works is iterative. You pick 10 points at random. You group all the vectors which are closest to that point. Then you take the average of all those vectors, and that's your new point for the next step. And you just keep repeating this over and over until you get a collection you like. In this case, iteration's kind of a hard thing to express in LINQ because it's all declarative and you set stuff up ahead of time. You can enumerate over a sequence, or in this case, what we've actually done is enumerate over a query. The step function here, actually, because it's all lazily evaluated, is going to take this input query and it's going to add a couple more operators onto it. So every time we execute this step function, we're going to get a new query back, a new iQueryable vector. Nothing has gotten run on the cluster. Nothing has been instantiated anywhere. just our query gets a little bit deeper, 2 levels deeper, every time we execute that step function. And then finally, at the end of this, when we call toPartition table, DryadLINQ sees that, and it can see the whole query, all 10 different levels of that query, instantiate the whole thing on the cluster all in one go, rather than having 10 different jobs going to the cluster. You bundled it all up into one big query, send it all to the cluster, it runs, it keeps the data partitioned for all 10 iterations, and brings back the results you were looking for. So it's kind of a very clever way to do these kind of iterative algorithms, is building up these very big queries programmatically. And I wanted to do an example where we just kind of put it all together, did a real world thing, put the data out in the cluster, and did some kind of basic mining across it. In this case, I said, I'm going to use this great data set that Major League Baseball has. They actually have every pitch thrown in a baseball game since 2007 recorded up there, who threw it, what the speed was, how much it curved, was it a strike or a ball, did it get hit or not. Fascinating, fascinating data set if you're into baseball. It's not stored in the most approachable schema, though. It's basically one XML file for every appearance by a pitcher. So you have an XML file. It'll have the pitcher who came into the game, the number of at-bats that he faced, the batter he faced, and every pitch he threw to that batter. And it ends up like almost 50,000 different XML files. And then there's an XML file for each player that has, height, weight, what their number was, what their batting average was. So that's another 6,000 XML files. They're all very small XML files, but there's a ton of them. So our approach here is we want to do some mining across this, and it's pretty tedious to attack these 47,000 XML files. And so what we're going to do is we're going to pull out the data from each file that we're interested in. We're going to partition this data across our cluster, and then we can run our DryadLINQ queries across that. So we'll use LINQ-to-XML to shred the XML and pull out the data we're interested in. We'll use DryadLINQ to partition the data across the cluster and to do the analysis of the objects. So this is the first thing we want to do, is we want to stage the data. In this case, I've got a list that was input. It's a list of 47,906 XML files. And I don't want to have one machine process all those files. I want to split that file processing across my cluster. So in this case, I've taken the file list, and I've turned the file list into a partition table. And I've actually done explicit hash partition on that partition table. So what that's going to do is for every file name, it's going to call get hash code on it, figure out which machine we're going to send that file to, and create a partition table chunk on that machine. So now we've got that data spread across our cluster. We can then in parallel, use LINQ-to-XML. We'll do a select many. I'm not going to get into the XML format here, but you can trust me on the LINQ.XML, and we'll pull out each at-bat out of each XML file. Then out of each at-bat, we're going to pull each pitch out, and we're going to create this final select clause here. We're going to create a new pitch object. Pitch object is something that I've defined. It just has a couple of fields in it: the pitcher ID, the batter ID, and the speed of the pitch, in this case. And we're going to turn that all that list of pitches into a partition file, a partition table. We're going to keep that on the cluster. Now we can do our analysis across this file that's been stored on our cluster. And we're going to do a similar thing with the player data here. The stage player data is going to take the 6,000 XML files. In this case, I didn't bother partitioning it across the cluster because it's only 6,000 files. It's not that big a deal. But we're going to turn that into a partition table as well. So now DryadLINQ can operate on both the pitch data and the player data. Once this is all set up, it's simple. We can now just use DryadLINQ, say, OK, order by descending, and then take the top 10. And give me the 10 or top 100. Give me the 100 fastest pitches that were thrown over the last 3 years. So it's drop dead simple. Once we have this stuff out there, once DryadLINQ can see it, you don't have to really think anymore about how the data is laid out, how it's partitioned. You can let DryadLINQ take care of the parallelism, the sorting, picking the top ones. And of course, since we support joins, now we can do some interesting stuff with the player table and the pitch table. So in this case, I'm doing a join across the ID of the pitcher. So now I can actually pull out the name of the pitcher out of the player table. It wasn't stored there, only the ID was stored in the pitch data. So I can do a join on the player ID, pull out the name. and then I'll do a distinct. So we'll throw out all the duplicates so we can see who are the pitchers who threw the fastest pitches over the last 2 years in Major League Baseball. Now, of course, you can do group buys and all sorts of other interesting stuff there. So what does this stuff look like when you run it on HPC server? We talked a lot about the DryadLINQ and the Dryad, but HPC server is kind of left out of the picture a little bit. So what actually happens is you run your DryadLINQ program in the client workstation. We do the develop, debug locally. You can even run these DryadLINQ jobs locally on your machine. There's a debug switch that says, okay, don't run it on the cluster, actually just let me debug it on my machine until you get it to working, and then you can flip the switch and send it off to the cluster. Then when DryadLINQ is actually going to instantiate the query, they do the code gen, does the query plan creation, and actually ends up submitting a job to HPC server. That job is just going to allocate all the resources it can, and it's going to run one task within that job. That first task is the Dryad Job Manager. Dryad Job Manager is the thing that's responsible for then scheduling the graph within the allocation that HPC Job Manager has given it on the cluster. So he's going to look at the query plan that DryadLINQ produced, and then he's going to start scheduling tasks for each vertex within that graph. So you see all these tasks show up in the HPC Job Manager scheduler as they're running, and you can see which stages your vertices are running where and how that's scaled out. It's kind of interesting output to look at, and some of these graphs can easily generate thousands, 10,000 different tasks running on your cluster in parallel. And finally, once all the tasks have completed, the job finishes up, your client application says, oh, my job's done. Now I can get my output results back right off the cluster. So what's this sort of stuff good for? We talked a lot about data mining, analyzing big server logs, pulling stuff out of Major League Baseball. So we do a lot of data mining at Microsoft, both analyzing security logs, analyzing all the Watson Squim data, all the bug reports that people send us when that little pop-up comes that says send data to Microsoft. We have lots of programs running internally that mine through all that data to find correlations, to find patterns. Graph analysis has turned out to be a really good sweet spot for this technology. Computing PageRank, I didn't put that sample up here, but it's similar to the k-means one where you have an iterative algorithm to compute PageRank of web pages. And image processing, a lot of these image processing kind of tasks tend to be, I have tens of thousands of files and I want to do some churn, some analysis across all of them. DryadLINQ is a really easy way to do the same kind of thing I showed with a baseball data set where you just partition the file names across your cluster, run your algorithm, produce your output you want, and then maybe you want to do some filtering or sorting or take the top 10 results or some kind of correlation on the output of your algorithm. The training decision trees, that kind of thing around machine learning. Simulations, Monte Carlo stuff, again, is really a good way to say, hey, I just got a big input data set, I got a big space I want to explore. I can just create a million different parameter inputs and then do a select across that to kick off the workflow for running all my different experiments in parallel. And again, the machine learning is pretty popular both for health solutions and image processing and some of the astrophysics stuff. So there's, as I mentioned, it's an incubation. There's a lot of work that's still going on. More advanced query optimizations, incremental computation. We have one of these big queries and then something changes. We want to respond to things in real time. Can we go back and just run those parts that need to be recomputed and keep the parts that were already run and don't have to change? Real-time streaming and event processing. How can we, right now, DryadLINQ is going to write its output to a file every time before it starts the next vertex. We want to get to a point where you can choose whether you want the availability and persistence of writing it to a file, or you'd rather opt for the performance of having, co-scheduling these two vertices and piping the data directly from one to the other. So we don't really have a good knob today to let you make that trade-off. I think people want that. And then global scheduling is a problem. These queries tend to be they change shape over time as they run. They get big, really parallel, and then they might have to scale down to a smaller set of machines. And you have multiple of these jobs running at the same time on a cluster. How do you share the cluster between these competing demands and get better throughput, as well as giving people kind of a guaranteed quality of service that they can make forward progress? Different storage providers. I talked about the partition file in detail. I mentioned the partition SQL table. We'd like to be able to plug in some other partition data stores underneath as well. So we'll be doing some refactoring to enable that kind of thing. We want to be able to take this up to the cloud, so you can take your Link application, run it locally, throw the P-Link switch, run on a multi-core, throw the DryadLINQ switch, run on a cluster, run it up on Azure in the cloud against some of the data sets we want to store up there. This is really ongoing research. And then debugging, performance analysis. How do you know when this thing didn't work? What went wrong? DryadLINQ is pretty nice that it gives you this abstraction and hides a bunch of stuff for you. But then when you're trying to figure out why it's taking so long, we kind of have to undo all that and let you get down to the bare metal and see what's really happening and how that relates to your input query. So there's a lot of work that I think we have to do there, some research as well. So these are all ongoing to-dos. Again, we're looking for additional feedback. If you guys tried out the things you like, things you don't like, let us know. We've got a Connect site up there. If you go up there, you can download it. I think there's a new release going live either today or very soon after today. It was going to be Monday, but there's one bug we fixed. So you can download the DryadLINQ source, binaries, samples. There's a bunch of sample codes. There's a blog up there. We're going to be posting some stuff regularly over the next few months. Discussion group for giving us your feedback. P-Link, underlying DryadLINQ is P-Link. This is pretty interesting technology. Like I said, there's a talk later in the week on specifically on just P-Link. I encourage you to go if that interests you. And this is in the .NET Framework beta too, so you can get this as the download. And then HPC Server 2008, all this stuff is running on HPC Server 2008. That product is based on Windows Server 2008. It's available. You can get evaluation copies at this site. So download it, try it, give us your feedback. Let us know what we need to change, what do you think is missing. If you have interesting applications, we'd love to hear about what you're using it for as well. It helps us make our product decisions. So that's all I have. Any questions? Basim, could let you in. The results from the baseball query. I should have put those in there. There's a pitcher for Detroit, I think. Zach somebody. I don't remember off the top of my head. And he was like through most of them. But there are the usual suspects. Justin Verlander is up there, JJ Putz, and a few others. And I think there were some radar gun calibration problems because I'd never seen a 112-mile-an-hour pitch, but there was one in that data set that might have been a bug. I don't know. Yeah, DryadLINQ doesn't make multiple copies as it goes on because a lot of these data sets are just transient, right? As you're executing the query, you don't necessarily want to make duplicate copies and double your I/O. And a lot of times it's faster to just rerun the chunks that you lost and back up the graph and rerun them and regenerate them. But you can create a partition file which has multiple replicas of the chunks. So I pointed out in the partition file example, there's a chunk number. You can just have the same chunk number can be in multiple lines on different machines if you wanted a data set that you wanted to be highly available and store multiple chunks.
I wanted to kick the tires on HPC server. What's the minimum hardware you should load it onto that would give you a meaningful experience?
The requirements for HPC server are just the same as Windows Server 2008, whatever I don't know off the top of my head what they are, but usually you probably want a cluster of 4 machines or so is interesting. You can have a cluster of 1 machine, but it's not so interesting, but 2 is okay. I like 4, but fits under your desk. I'm under my desk. Well, we're not using the SOA broker in this architecture. So all the communication is in this framework right now is done by writing files to disk, reading those files from disk in the other vertex. So, yeah, and back. Well, we use most of the stuff is all generates the Lambda expressions. So we rely on the Lambda to generate the closure over the Lambda. And then we take that and bring that into the query. Does that answer your question? I'm not quite sure what your question is, but. Well, we'll do a closure over the locals, right? So they'll get closed. But if you have expressions with side effects, it's not gonna work. So we tend to assume that the thing is functional, doesn't have side effects. The local variables are treated as inputs if you're using them, right? So then we get serialized and put into that code that DryadLINQ generates, the C# code that gets compiled and sent down there. But if you write to those variables and expect in your expression and expect to read them later, they're not going to be there because we don't bring them back to the application. Yeah.
You're using SQL as one of the storage providers. Do you guys take into account the statistics from those nodes when you're generating the graph? How do you optimally plan the graph?
I don't know the answer to that question. The SQL stuff is really, I would say, still kind of experimental at this point. So we're still working out some of the stuff there. But I don't think there's anything fancy going on. We're just taking the SQL and sending it to those machines in parallel. So, but we do look at the data that each vertex input and output data that gets generated. So when we do repartitioning, we can repartition to balance the load out. So we take the data sizes into effect. But we don't really do anything based on. Yeah, Dryad does that as it repartitions stuff. If all your data ended up on one machine, say, oh geez, we got to do a repartition. And it also does aggregation at the rack level, where if you don't necessarily want to do an aggregation over the whole cluster, you want to do sub-aggregations of the data and then aggregate the sub-aggregations. So it does those kind of dynamic things at runtime as well. Anything else? All right, fill out your feedback forms. It's important. We send $1 to Boys and Girls Club, I think, for every feedback form you send in. So fill them out, send them in.